This is section 9.1 of Rosen, Relations and Their Properties, and we're going to talk about creating new relations from existing relations. Here we're talking about relations from sets to other sets. So relation 1 and relation 2, since they are subsets of a Cartesian product, we can use our operators on sets to create new relations. I can take the union of two relations if they come from and to the same set. I can take their intersection. I can do set differencing to create new relations. So here I have two relations from A to B, and you can see that they are subsets of their Cartesian product. I can take the union of them to create a new relation. So that'll be all the unique elements that are in either of them. The intersection, there's only a single element that is common to both. And the set differences in either direction creates new relations from A to B. Okay. Another action we can do with relations from sets to sets is compose them. So I have two relations, R1 from A to B and R2 from B to C. If the second relation in one of them is the same as the first relation in the other one, I can create a new relation um, from the first set to the first set of one to the second set of the other. So we say that the composition of two relations, in this case R2 with R1, is a relation from A to C, where when xy is a member of R1 and yz is a member of R2, then xe is a member of R2 composed with R1. We put the relation that acts second to the left and the relation that acts first to the right. So R1 is a subset of A cross B. R2 is a subset of B cross C. And R2 composed with R1 is a subset of A cross C. What is R1 composed with R2 in this example? Well, it's undefined because A does not equal C, at least as far as we know. Okay, here's an example of composition. Here I've got R1, and I'll say this left set of elements is my set A, and this right set of elements is my set B. And we can see that it has two elements in the relation, the ordered pair AP and the ordered pair BM. All right, now let's consider a second relation from the set B to the set C. We'll call that R2. It has three ordered pairs, NW, MX, and MZ. So the question is, what is the relation R2 composed with R1? Well, it'll be a subset of A cross C, Cartesian product of A and C, but it won't have any elements that begin with A because P does not have, there's no ordered pair in R2 that starts with P. So, but B goes to M, and R2 does have an ordered pair that starts with M, two of them actually, MX and MZ. So the composition will contain BX and BZ. Okay. Now the concept of composition can apply to relations on a set. In that case, it gives us the concept of a power of a relation. So if R is a binary relation on A, then the powers of R r to the n, are defined. Well, r to the first is defined as the relation itself, and r to the n plus 1 is defined iteratively or inductively as r to the n composed with r. So r is a subset of A cross A, and r squared, I'll say r composed with r is a subset of A cross A. And we say that r squared is equal to r1 composed with r, which is just r1 is just r cubed is equal to r squared composed with r, etc. So by this means we can use composition to talk about powers of a relation. They have an important property related to the transitivity property. Powers of a transitive relation are subsets of the original relation. So that's a way we can check to see if a relation is transitive. So relation R on a set A is transitive if and only if all powers of the relation are a subset of the original relation. There's an elegant proof of this in your text, but it uses induction, which we haven't covered yet in this class. But I recommend you take a look at it. And that is section 9.1 of Rosen.